Today, in this video lecture, we will see relation between shear force, bending moment and intensity of loading. In our previous lecture, we had seen basic concept of shear force and bending moment diagram. Now, consider a beam and take two sections at here and consider this small element as delta x. And this is detail A. And draw detail A bottom. So, this is delta x, small element of that whole beam, and consider that this element have transversely acted uniformly distributed load along the delta x length, and see shear acts at this part is V of x and shear act here is V of x plus delta x, and moment act here is m of x and moment acts here is m of x plus delta x. Now consider this is in equilibrium and we have to find relation between intensity of loading and shear and intensity of loading and moment. That means how shear force V of x and m of x vary. So first draw equilibrium equation. Summation of force in y direction is equal to 0. See y direction forces. This is V of x is vertical force. This is V of x plus delta x is also vertical force, and this is loading. Loading is W of x. So downward direction is negative and upward direction is positive. So minus V of x plus V of x plus delta x minus W of x into delta x. Equal to 0. Now rearrange it mathematically. This V of x plus delta x minus V of x and equal to W of x delta x. So this delta x take here in denominator, W of x. This W of x is intensity of loading. See here, W of x is intensity of loading. And now limit of delta x tends to 0 is, see this, limit of this is dv by dx, and this is W of x. So this one relation we get from vertical equilibrium equation. Intensity of loading is equal to dv by dx. This equation, remember this equation, dv by dx is equal to W of x. We will see meaning of this equation. Now next take moment. See, if we take moment here at this point, that means this v get cancelled, and moment at here, that means this v of x and this w of x acts. And if we take moment here at center, that means let's assume this as O point. That means see, this w of x delta x get cancelled because this is in equilibrium. This wx is acts like this, and this is like this. That means this is in equilibrium. Only force acts are this v of x plus delta x, and this m of x and m of x plus delta x. Now take moment at point O. So see, consider clockwise as positive and anti-clockwise as negative. So this mx is clockwise, so plus mx, this m of x plus delta x is anti-clockwise. That means this is minus m of x plus delta x. This v of x is also anti-clockwise through that point O, so minus v of x into delta x by 2. This distance is delta x by 2. And this force v of x plus delta x is also anti-clockwise. That means minus v of x plus delta x into delta x by 2. Movement is force into lever arm, force into perpendicular distance to that force, so equal to 0. So multiplying this equation by negative sign on both sides, minus m of x plus m of x plus delta x plus v of x into delta x by 2 and plus v of x plus delta x into delta x by 2. So again, dividing this equation by delta x by 2. Dividing both sides by delta x by 2. That means rearrange this as m of x plus delta x minus m of x divided by delta x by 2, and this term take right hand side, and this delta x by 2 get cancelled. That means equal to minus v of x minus v of x plus delta x. So this m of x plus delta x minus m of x upon delta x by 2 is equal to minus v of x and minus v of x plus delta x. So if we limit this, limit delta x tends to 0, so see this delta x get 0. It means here minus v of x and minus v of x is minus 2v of x, and this value gets dm by dx. So dm by dx is equal to minus 2v of x. So dm by dx minus 2v of x. See, this is not only dm by dx, this is upon 2 also. So these 2 get this side. So 2 dm by dx equal to minus 2 v of x. So this 2 get cancelled. Dm by dx is equal to minus v of x. So this is another equation we get. This is another relation between moment and shear. And this is equation between intensity of loading and shear. So by using this equation, intensity of loading and shear dv by dx is equal to w of x. See, dv by dx is equal to w of x. Put this vx value here. So d, that means vx means minus dm by dx, and this is dx, this is w of x. So this value is like this, d m, this is d square m by dx square, d square m by dx square is equal to minus w of x. So this is third relation between intensity of loading and moment. See, we get three equations. Intensity of three equations between shear and moment, between intensity of loading and moment, and between intensity of loading and shear. So write these three equations here. So we will see these three equations. dv by dx is equal to wx, intensity of loading, dm by dx is equal to minus v of x, and d square m by dx square is equal to minus w of x. So see, these are relationships between intensity of loading and shear, between shear and moment, and between intensity of loading and moment. Now see this first relation, this intensity of loading. If this intensity of loading is 0, that means this dv by dx is also 0, but this v is constant. See, with the help of example, this is simply supported beam and carrying point load at center. W. Here W by 2 and W by 2. See this part, loading is 0. That means shear is constant. So shear force diagram is like this. Constant. Constant where there is no loading. See here also. No loading. Here constant line. Here constant line. And if this W of x is constant, that means this dv by dx is also constant, but this v is linear. And see this also. See another example. This W is uniformly distributed, constant throughout its length, W per unit length. So see this W is constant. Now its shear force diagram is linear. See, linear. That means this is linearly varying. Here shear loading is 0. That means here shear force line is constant. So this is the relation. And now see this dm by dx is equal to vx also. If this vx is, see, if this, we can see this here. See, this is linearly varying. That means this vx is linear. That means this dm by dx is also linear, but this m is one order higher. That means this is parabolic. That means this comes like this. WL square by 8, and this is WL by 2. And see relation between moment and intensity of loading, it is 2 order higher. If this is constant, then this is parabolic. See shear and moment, there is 1 order higher relation. If shear is linear, then moment is parabolic. If shear is constant, then moment is no. If see this first relation, if loading is constant, then shear is linear. dv by dx is equal to w of x, and dm by dx is equal to minus v of x, and d square m by dx square is equal to minus w of x. That means see relation, this dv by dx is equal to w of x, and dm by dv by dx, sorry, Yes, dm by dx is equal to minus v of x. It's go back from, we calculate from loading, we calculate shear, and from shear we calculate moment. So go from loading we calculate shear, and from shear we calculate moment. So relation is like this: shear loading dv by dx is equal to w of x, and dm by dx is minus v of x. Here minus sign comes, and here d square m by dx square is equal to minus w of x. This is like this. Thank you very much. Concepts related to shear force and bending moment diagram. See, first bullet point: positive value of shear force and bending moment are plotted above the baseline and negative below the baseline. This point. So for that, see with the help of example, consider this as a simply supported beam with point load at middle. That means reaction gate W by 2, W by 2. So this point tells us positive value of shear force and bending moment are plotted above the baseline and negative value below the baseline. So this beam is baseline, and see shear force diagram of this beam is, this is beam with loaded, with loading, and this is shear force diagram. So see, this diagram is like this: this is positive, this is negative, and this is baseline. Meaning of this first bullet point is this: positive value of shear force and bending moment are plotted above the baseline, this is baseline, and negative below the baseline. So now second point is, if there is no loading between any two sections, the magnitude of shear force will not change. No loading, magnitude of shear force will not change. See, here there is no loading, so magnitude of shear force is also W by 2, same. Between the given, if there is no loading between any two sections, the magnitude of shear force will not change between the given section, and shear force diagram will not change between the given section, and SFD will be horizontal. See, this SFD is horizontal. Now third bullet point is, if there is a vertical load or reaction at any section, the shear force at the section will suddenly increase or decrease depending on the direction of vertical load. See, in this beam here, this is concentrated point load, and see shear force diagram here. This is suddenly decrease because of this concentrated point load is in downward direction. So this suddenly decreases. So this is meaning of this third bullet point. Now next is, if there is a uniformly distributed load between two sections, the shear force diagram is inclined line. See similar beam, simply supported, but here loading is uniformly distributed. Now due to uniformly distributed load, this is beam with loading, and this is shear force diagram. So due to this UDL, kilonewton per meter, this shear force diagram is maximum at support and minimum at center, and this is inclined line. positive, negative. So this is meaning of this first bullet point. Now next bullet point is, if there is uniformly varied load between two sections, the shear force diagram is parabolic line. See, uniformly varying load, that means like this. So shear force diagram is parabolic, that means like this. Not a straight line, parabolic line. If there is a couple in loading diagram, there is no effect of it on shear force diagram. See, if there is couple here, couple movement here, there is no effect on shear force diagram due to movement or couple acting on that beam. Next is variation of bending moment diagram is parabolic for UDL. Bending moment diagram. Now we will draw bending moment diagram. Here at center WL square by 8, and it is W per unit meter. W per unit. So bending moment diagram is parabolic for uniformly distributed load. Variation of bending moment diagram is cubic for UVL. Now for uniformly varying load, it is cubic. Variation of bending moment diagram is suddenly increases or decreases at any section having couple, and it depends on nature of couple. If here movement, we will see this in our solving examples. If here movement, then bending moment diagram suddenly increases some point like this, and then this two increases or decreases as per couple. Bending moment at free or simple end is always zero. See here, bending moment is zero. Here, bending moment is zero because it is some simple support like pin or roller. But at fixed support, there is movement. For fixed, if this beam is fixed, then there is movement occurs here. If this beam is fixed, then movement diagram is like this. Hogging movement generate and sagging movement generate. This is negative, negative, positive. In case of overhanging beam, point of contrapicture must be located. Bending moment at this point is equal to 0. Point of contrapicture, that means consider this as a overhanging beam with uniformly distributed load. So due to this, see, movement changes its signs here, and this is point of contrapicture. In case of overhanging beam, point of contrapicture must be located. Bending moment at this point is equal to 0. Where there is point of contrapicture, bending moment is 0. Maximum bending moment occurs at the point where shear force is 0. For that, see again. This is beam. This is SFD. See here, shear force is 0 and maximum bending moment occurs here only, where there is shear force is 0. So this way this topic is complete. Thank you very much. So see through table, no loading between two sections. We have seen no loading between two sections. That means shear force diagram is horizontal line. We had seen that simply supported beam with point concentrated load at middle, shear force diagram is horizontal line there, because there is no load between that left reaction to that middle point, and bending moment diagram is inclined line. Uniformly distributed load between two sections. We had seen simply supported beam with UDL also. In that, shear force diagram is inclined line and bending moment diagram is parabolic line. Third is uniformly varied load between two sections. Here, in uniformly varying load, shear force diagram is parabolic line and bending moment diagram is cubic line. Remember this. For UL, SFD is parabolic and BMD is cubic. Fourth is point load at a point. Shear force diagram, there is rise or drop at that sections. We had seen this also. And couple at a point, when there is couple at a point, bending moment rise or drop at that point. And for internal hinges, no effect in SFD, but in BMD, when there is internal hinge, then bending moment diagram is 0. So remember this. Thank you very much.